In this video lesson, we are going to look at the reactivity of various hydrocarbon families. Okay. Now, unfortunately, we did not. Normally, we get a chance to do this simple reaction where cyclohexane, cyclohexene, and toluene, their reactivities are compared by reacting them with bromine or potassium permanganate or sulfuric acid. Okay. And what we derive from this is that alkenes, using cyclohexene as the example, are very reactive, whereas alkanes are not. Okay, so cyclohexane doesn't react, cyclohexene does. And then secondly, benzene and benzene derivatives are minimally reactive, although their structure indicates the presence of multiple bonds. So we got to kind of try to figure out what is going on here. I would have expected, just by looking at cyclohexene, this has got a double bond. If that reacts because of the double bond, the toluene should react even more because of the multiple double bonds, alternating double bond system that it has. Okay, so let's try to explain those two observations from the simple activity. Firstly, alkenes are very reactive, whereas alkenes are not. So why would that be the case? Okay, so one thing that we can kind of realize is that alkenes have an extra pair of electrons between one pair of carbons, whereas alkenes do not. Okay, we saw this true when we were producing polymers there in the kinetics unit, that things with double bonds tend to be able to react because they maintain a bond in between those carbons, even if you remove the second bond in that double bond. So as a result, one of the bonds in the double bond reacts, and the carbon-carbon chain will still be maintained. So I'm just going to use the reaction between cyclohexene and bromine as an example. So this is kind of what would happen. Okay, so one of the bonds in the double bond, so let's say this one that's sticking out here, is going to react with bromine. So this is how it does it. This is called an addition reaction. Okay, so this double bond will try to, it's a pair of electrons, it'll try to connect to that bromine, and when it does, bromine only wants one bond. So this bond needs to break. And it makes sense because this carbon right here, if we're going to form a bond in this place, this carbon is going to be missing a bond, so that pair of electrons can be used to produce the necessary bond for the second carbon here. Okay, so we'll end up getting a structure that looks like this. And in practice, bromine's quite orange. Okay, this is colorless. When it reacts, it produces this alkyl halide, cyclohexene with two bromines on there. This is colorless as well. So you'd see a decolorizing of the bromine that's present there. Okay, so this reaction works because of that extra pair of electrons, and it undergoes an addition reaction. This doesn't happen with cyclohexane. Cyclohexane, if it were to break its bond in between in the same way that cyclohexene does, we would lose the bond between those two carbons. Okay, we would get something that would look like this, and it would no longer be cyclic structure. We'd lose that bond, so it's no longer connected, and it just doesn't happen. Okay, so that's one reason why alkenes might be more reactive. There's more evidence there too. So evidence from bond dissociation energies, okay, from our thermochemistry unit, indicates that the two bonds in the double bond are not the same. If we look in the table, just a single bond between two carbons, which we know is a sigma bond, has a bond dissociation energy of 348. So that's how much energy is required to break it. We have a double bond, it's 640 to break those two bonds. 614, I mean. That means is if I took the difference, the second bond's energy, we consider them being the same, which they technically are. This is a single bond and a sigma bond. This is a sigma and a pi bond. If I subtracted these, I would find out that that second bond that's present has a smaller dissociation energy than the first one does. Okay? So what that indicates is there's a little bit less energy required to break it. So that second bond, which is the pi bond, is a bit weaker. Okay? Adding to that, we do know that when we have multiple bonds, we start having different types of bonds from molecular orbital theory, okay, where bonds are actually the overlap of orbitals with single electrons in them. And that's how we produce these bonds, and they're called molecular orbitals now because they're forming orbitals in molecules, okay? So the quantum mechanical model of a C double bond, CC double bond, it illustrates that the two bonds in the double bond are not equivalent. If it's just a single bond, like in an alkane like this, the single bond is a direct overlap of two orbitals, which we call the sigma bond, okay, or this sigma letter, the Greek letter. Okay, that's this thing right here. This is the sigma bond. When we have a double bond is produced by one sigma bond, which is direct overlap like we have here, and a second bond that has two parts, a top lobe and a bottom lobe, which is our pi bond. Okay, and together we get two bonds out of it. It is stronger than just a single bond, but that second bond is weaker than the first one is because it's a different type of overlap. It's a little bit weaker. It's harder to hold those two atoms together because it's not right along the bond axis. Okay? So, as a result, if we kind of consider all this information, the quantum mechanical model shows that the second bond in a carbon-carbon double bond is a pi bond, which points above and below the carbon axis. As a result, the pi bond is more easily accessible as well as to a reactant and appears like a fluffy cloud of electron density above or below that can be used and capable for a reaction, while at the same time maintaining the sigma bond and holding those carbons together, which is much stronger. Okay, so that's the idea or why alkenes tend to be more reactive than alkanes. Now, the other puzzling thing is, although toluene, now you got to remember, toluene, we can't use benzene, that would be the ideal, but toluene has a methyl group, and it's this benzene ring, 6-membered ring, okay? Cyclohexene is a 6-carbon cyclic structure with a double bond, and cyclohexane, 6-membered cyclic structure with only single bonds. Okay, you'd expect if this is reactive, this would be even more reactive. It's got 3 times the number of double bonds. But this is not what we see. We see that toluene is minimally reactive. Okay, benzene and benzene derivatives are only minimally reactive, although their structure indicates the presence of multiple bonds. So why is that the case? Well, what it does suggest is benzene and all aromatics must be more stable than alkanes, okay, if that's the case. If it's not reacting, it is going to be more stable. So these aromatics are more stable than the alkenes themselves. And they can't actually be, it's kind of suggesting that there is quite a bit of difference between these two. So how does that kind of play out? Although benzene appears to have 3 double bonds, they don't behave like individual double bonds. Otherwise, benzene would probably be 3 times as reactive. So what it's suggesting is that in benzene, the double bonds aren't real double bonds. What does that mean? Are we going to rationalize that? Well, let's kind of go a little further and see if that kind of makes sense. There's some more evidence here too, other than just what we saw. Evidence from crystal structure of carbon-carbon single bonds and carbon-carbon double bonds indicate that these bonds are all different lengths. Okay? But when we put them in, so this one would be shorter than these single bonds. Kind of makes sense. You got two sets of overlap. They're going to hold the atoms closer together. But when we look at benzene, all the bond lengths are the same. We don't have a short one here and a long one here. Short, long. They're all identical. Okay? So let's illustrate this a little bit. So if I look at cyclohexene, okay, the length here, and we're going to use angstroms, which is 10 angstroms make a nanometer. Okay, it's a classical unit. So this is 1.3 angstroms if it's a double bond, whereas if it's any of these single bonds here, it's 1.5. So a little bit longer. This one's a little bit shorter. So we would expect, like I was saying there before, that we would have a short one, 1.3, and a long one, 1.5. Just kind of twisted this a little bit. 1.3, 1.5, 1.3, 1.5. And that is not the case. But actually, benzene has this structure. It is perfectly symmetrical, and every single bond length is 1.4, all identical. What does that tell me? Well, a couple things it can kind of tell me here. The bond length is kind of halfway between a double bond and a single bond, and they're all identical. So they all have the same type of bond. So bond is somewhere here, all same length. So the bond is somewhere between a single and a double bond length. Okay, so something mysterious is happening here a little bit. A little bit more evidence. If you were to look at the heats of hydrogenation, which basically involves taking away the double bonds with hydrogen. Okay, so we're going to saturate this. If I do that with cyclohexene to make cyclohexane, this energy would be negative 120 kilojoules. But if I do this with benzene, if these were all independent double bonds, you would expect it to be 3 times the amount, would you not? I'd say so. You'd expect 3 times negative 120 kilojoules per mole, which would be negative 360 kilojoules. But the actual amount is negative 210 kilojoules per mole. So they are definitely different. They're not all individual double bonds. Somehow they're interacting with each other. Otherwise, this would be fairly close to being correct. But one more consideration that we talked about at the start of the course was resonance. With some of these structures, if we have double bonds, if there's an alternate order or way that we can write or draw these double bonds without moving the atoms around, just by moving electrons, we can allow electrons to be pushed around into different positions. So that pair of electrons, I don't want to do both of them because that would disrupt this bonding. But I can move this pair of electrons, one of the double bonds, over here. That would leave an empty spot here. I need another bond for that carbon, and this one would be fine, but I'd have too many here, so that's going to push these electrons over here, and likewise these electrons over here. When that happens, I end up producing a similar structure. Atoms are all the same, but with double bonds in the alternate positions. And we talked about this, that this could revert back and then go back. And it's kind of like almost like vibrating between these two different structures. Lewis structure was. But really the true picture of this molecule isn't this, then this, and back and forth. It's a mixture of these two, which we call a resonance hybrid. So that half the time, so we still have single bonds or sigma bonds all around, but half the time we have the second bond in this position and second bond here. Half the time it's along this carbon-carbon bond, and half the time it's there. Half the time it's here, and half the time it's there. Okay? Or we may want to even just draw it with a circle to represent that. So this is that resonance hybrid. And if I wanted to maintain the colors here, it would be this double bond is half the time here and half of the time there. Half of the time here, half of the time there. Half of the time here, and half of the time there. Okay? But if we even go a little step further and introduce our ideas of pi bonds, we get an even better picture. We realize that along the carbon-carbon axis of all around the entire benzene ring, we've got sigma bonds connecting all the carbons, and that's going to stay the same. But we've also, because we got a double bonds everywhere, we've got p orbitals that are found above, the lobes above and below the ring, okay? And so even better than having just a pair of electrons, pair of lone pairs making a bond. Those electrons that are found in those double bonds, so 2, 4, 6 electrons, are shared within the whole ring, okay, above and below the surface. And so we get this ring structure that we're trying to show here, and it's a delocalized bonding system for those conjugated, and these are called conjugated alternating double bonds or conjugated double bond system. So when we consider the quantum mechanical model of benzene, the second bond in each of the double bonds is composed of sideways overlap of the p orbitals. This doesn't produce 3 individual pi bonds, rather due to the proximity and the symmetry of the structure, the p orbitals share electron density throughout the entire structure. So this makes this very stable, and why we don't need as much energy to be able to convert it into a cyclohexane. Okay, or not as much energy is released when we convert it into cyclohexane. Okay, rather due to the proximity, is that entire structure. This is known as delocalized pi bonding system and contributes to the stability of all benzene molecules, including the ones we saw in the structure. In fact, it also explains how the structure is not simply 3 independent double bonds, but an alternating double bond system that acts as one unit. Okay, so this is all these things point to the fact that benzene is not 3 individual double bonds and 3 single bonds. It is actually a system of double bonds that interact together, okay, and with different views to help us understand different bits of information and evidence that explain this difference in that reactivity than what we would expect.